Now if we have, let's just say 3 masses, we could have any number of masses. We're going to get excuse me, an expression here for any number of masses, for the situation of any number of masses. But here's your axis of rotation. We're rotating in one direction or another around the axis of rotation. We got mass m1 at distance r1 from the axis, mass m2 at distance r2 from the axis, mass m3 at distance r3 from the axis. And we have an angular acceleration alpha. We want to know how much torque is going to be required to get that angular acceleration. Well, we need the torque that enough torque to accelerate this mass, and enough to accelerate this mass, and enough to accelerate this mass. So we're going to add the torques necessary to accelerate all 3 masses. So how do we get the net torque? Well, we find the torque to accelerate one mass, and if we know r for any mass, let's just start by finding the torque to accelerate one mass. And let's say now the masses are mass 1, 2, 3, maybe we don't have more than 3, maybe we got 10 million masses, okay? We've got some number of masses. Let's just figure out the torque on the ith mass. Okay, so generalizing to where we have whatever number, if I is the index of the mass that we want to find, if I is the number of the mass, if the masses are numbered 1 through 10 million or 1 through 3, it doesn't matter. I is some number between 1 and whatever number of masses we have. For mass m sub I, it's going to be at some distance r sub I. Now we're of course assuming these masses are actually particles or sufficiently close to particles not to make any difference. So though, for mass m sub I at radius r sub I, what do we have? Well, we take the angular acceleration in revolutions and in radians per second, and we multiply by the radius, the distance from the axis of rotation, and now we have the acceleration in meters per second squared, because when we multiply the radius by a radian of angle, we get let me say that again because I left something out. If we multiply the radius, say in meters, by a radian of angle, as in radians per second squared out here, multiplied by the radians of angle, we get an arc distance in meters. If Ri is in meters, our arc distance is in meters. If Ri was in centimeters, of course, our arc distance would be in centimeters, and the result would then be an acceleration in, say, meters per second squared or centimeters per second squared, whatever the units of Ri are per second squared. Then Newton's second law tells us that the force required to accelerate that mass is the product of the mass and the acceleration. Furthermore, the torque that we get from that force is equal to what? It's equal to the force multiplied by its distance from the axis. We're assuming, of course, that the force is perpendicular to the moment arm or to the beam. Okay, so we multiply the force by the radius and we get the meters times newtons of torque. So we have these 3 relationships that we combine rather easily. So if we want the ith torque, what do? Well, we take the ith force times the ith radius. What's the ith force? It's the mass, ith mass, multiplied by the ith radius. So we replace the force with this expression. We get ith mass times the acceleration, and we multiply that by